Okay, so there were two options, right? There's two graphs. They're both, one of them is the training error, one of them is the testing error. Which one is which? And you said what? Oh, okay. So pretty split, 70%, 2/3 of the class said one thing, 1/3 of the class said the other thing. 2/3 of the class said the red is the test error and the blue is the training error. And 1/3 of class said the reverse. So it seems like you guys have a slight preference toward red is the test error, but not super confident amongst the class. Let me reveal the correct answer. The correct answer is that red is the tested error. So most people were right. When you see a graph like this, you should be able to intuit, like if you have a good understanding of underfitting and overfitting, you will have a good understanding of what is going on here. And the thing I want you to think about is how well, when you make the window size really small, how well does the purple function fit the training points? So the training points are these black points over here. What happens when you make that really small versus when you make it really big? And it kind of matches the story of underfitting and overfitting. What I think would be instructive now, since because only 2/3 of the people got it right, take 2 minutes and talk to the people near you and talk about what made you choose what it was. If you chose the blue one, then you were missing something. So try to figure out what you were missing and update. If you chose the correct one, maybe you can help the people near you. Maybe you can solidify your answer if you were just guessing. But let me give you a couple of minutes to talk to each other and kind of explain why the right answer is the right answer in your own words, and then maybe maybe there's some good idea that will come out of that. Okay, I'm gonna give you a little bit of time to chat. Let's say 2 minutes. Why is the right answer, and what is going on?
Exactly to the training data.
Okay, let's come back together here. I put it on the blackboard so we can add little notes and things, and I added the true labels, which is test and train. Before I say anything else, sometimes it will look like this. So the graph is correct, but oftentimes it will actually look like this as well. So I made it deliberately kind of tricky, where it wasn't clear which one was better. Very often, the test error is a lot higher than the train error, and then it's kind of obvious that the which one is which. But sometimes it can look like this, and then you got to go based on the shape. So both of these things are possible. It just depends on random chance which one will happen. But does anyone have a nice way or a nice story they told to convince themselves which one is which or what's going on here? Yeah.
Sir, because as we looked at, the correct answer is red is the test error and blue is the train error.
Right.
So the test error will decrease as the value increases because it is a completely new values we are putting into the
Which error will decrease?
test error.
The test error will decrease as you do what?
The values to the RMSE and when we calculate the average.
Okay, so you're saying the test errors will decrease and decrease and they'll get smaller and smaller and smaller.
Yes, sir.
I think that's wrong. So the test error goes down for a while and then it kind of reaches a minimum. And then it starts to go back up again. So the test error is the one that has this balance that you have to do, where you don't want to make it too big or too small. And in fact, we labeled this last time. We were talking only about the true error. The true error is supposed to be like the test error. So why don't let me add a category for the true error. And the true error is what we actually care about, is what we actually studied. And the hope is that the true error and the test error are related. So the true error is supposed to also go like this, okay? And we said last time that we had this spectrum. On this side, we were overfitting. And then on the other side, we were underfitting. This is underfitting on this side. And the point that we talked about before is that if you're underfitting, that's like a straight line estimator. You're not being influenced enough by every individual point. You're kind of looking at all the points together, and you're not doing as good of a job as you could. That's why the error is a little bit higher than in the middle. And when you're overfitting, you're kind of chasing the training points too much, and you're also doing bad. So this was the point that we made before. And it kind of also applies to the training set. Let me show you the picture one more time, right? So this is underfitting when you have a really large window size. You have like a flat line that's getting a lot of error because you're sort of not influenced by every point individually enough. You're kind of looking at too many points at once, and that's bad. That has a lot of bias, we said. And on the other hand, if you kind of make a really, really tiny window, then you're doing this crazy up, down, up, down, up, down, and you also have a lot of error. And that had a lot of variance, we said. So on average, you're getting each point on average right, but because you're so influenced by individual data points, they sometimes, by chance, really throw you off. And you also have a lot of error. So that is this picture that we had before, and the same kind of thing applies to the test set. The thing you said is that the error is getting smaller and smaller and smaller, and that is true for the training set. So that in the training set, if you look at the size of the error, as you make the window size smaller, it looks like it's always getting better, right? So the training error is decreasing this way. The training error decreases. And some people might even use the fancy word monotonically. Monotonically. So this is a common feature in data science problems, is there's often a knob you can turn that will make the training error smaller and smaller and smaller. Okay? So in this particular problem, the knob you can turn is the window size. If you make the window size smaller, you make the training error smaller. You make the training error smaller. And you can see that if you make the training error small enough, you will perfectly fit the data set. So here I made the window size super tiny, and look at the training error is how far away my purple estimate function is evaluated at the training points, at these black training points. And you can see I got it perfect. That's like a training error of 0. How much error do I have here? Well, the true answer was 0, and not the true answer, but the training point was at 0, and I said 0. And up here, the training point was at 13, and I said 13. So I got all the training points perfectly correct. My training error is 0. This, I think, is another really common misunderstanding of what data science is. If it wasn't for this issue, data science would be so easy. You just turn the knob as much as you want, make the error as close to 0, and then you're done. But the problem is having low training error is not what you want, right? So even though in the graph, you look at this and you're like, look, I can make the training error as small as I want. If you don't know any better, you say, that's good. Really make the training error as small as you want. Fit the training sets perfectly. Have a root mean squared error on the training set, which is 0. So fantastic. But that is bad. If you have a really good training error, that does not mean you have a really good test error, and it does not mean you have a really good true error. Those are the things you actually want. So this is like the pit of despair. Let's give it a cool name. Pit of despair. Where you made the error as small as you could, but on the training set, that is not what you want. And in this particular example, you can see exactly why it happens in the picture, right? If you make the window small enough, then around every point, that's the only point that you're looking at. So the window size is so small that you're always averaging exactly 1 point. So the value at the training point is always the value of that training point, right? So every little window contains exactly 1 point. So of course you get the training data perfectly. Okay. So this is the thing to watch out for. This is like a big red flag. If you don't understand this thing, that you don't always want to make the training error small, then you will make lots of mistakes in real life. I like this example. This one to me is like the clearest place to see it is with this window size. I'll give you another example in a second, but this is a good one to understand. Are there any questions or comments about this idea of the training going down to 0? So this is something you got to watch out for. Let me give you the other analogy that some people like. Imagine you are a student and you're studying for your arithmetic class. Student studying for arithmetic class. That's like grade 2. Okay. Okay. And you have a training set of problems. It's like 2 plus 3 equals 5. That's the left-hand side is the x, and the right-hand side is the y. And then there's another problem like 4 plus 1 equals 5. And then there's like another problem, which is like, what is 7 minus 2? It's 5. And then what is, let's think of another one. 1 plus 4, that's also 5. So if this is your training set, one thing you could do is memorize that the answer is always 5. You're like, I memorized it, I got it perfect. My score on the training set is 100%. I got all of these problems right. Was this one 5? Yes. 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 100%. Pat yourself on the back. Did a good job studying. And then test day comes, right? And here is the test set. Someone comes and tests you, and they say, what is, 6 minus 3? And then you're like, whoa, it's 5, because the answer was always 5. So even though you had 0 error on the training set, you didn't learn the right thing, right? You didn't actually learn how pluses and minuses work. You just memorized the answers, and you had a 100% score on the training set. You're going to get a very bad score on the test set because you didn't actually learn what happened. In this particular case, I would say that it's kind of the fault of the teacher. They probably should have given you some problems where the answer was something other than 5. But this is a great example of why can the training error be so low even if the test error is high? Because it's possible to memorize the training set without learning anything about what's actually going on. And that's what's going on over here. So this is really like an extreme example of overfitting when you memorize too much of the training set and you don't generalize well to the test set. Okay, that's one example. There was another example in the textbook that they talk about this one a lot in the textbook. And in the textbook, they draw graphs. Actually, maybe I have it. Maybe I have it in Mathematize. Let me see. No, okay, let me just draw the graph. Okay, so they have something here where they kind of call this the flexibility of the model. There were some graphs like this, the flexibility of the model. And they'll say like 2, 3, 4, and the flexibility is some number in their world. Maybe this is like 100. And then again, they draw the error. But for them, the window size is nice because it can be any number. Like it can be 2.1, it can be 2.2, but the flexibility that they were using in those examples was an integer, and they had the same kind of situation. So the test error was looking like this, right? But the training error was looking like this. The training error just always goes down. So it goes, let me draw them in the same column. 2, 3, and the test error, the training error, just goes down, 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 and eventually it hits 0. This is the train error. And this is the test error. So the difference in this example was that the thing they were using as flexibility had to be an integer. It had to be 2 or 3 or 4. It could not be 2.5. And the thing they were doing is the degree of the polynomial. So they're saying, I'm going to take my data points, and I'm going to draw a polynomial that goes through them as well as it can, and the degree of the polynomial is what I'm using. So they used the degree of the polynomial. So this is like fitting a polynomial to your data. That would be another way to do it. And you can see that if you use a large enough degree polynomial, if you have a polynomial that starts with x to the 100, then you can fit 100 data points quite easily. In fact, in our problem, because we have 30 data points, oh boy. Let's see if I can find what we actually want. Math test. Okay, great. So we have 30 data points. When you have 30 data points, a degree 30 polynomial will go through the 30 data points perfectly. So it'll be a polynomial something x to the 100 plus something x to the 29 plus something x to the 28, and it'll snake through and get every single point. But that will have 0 training error, but it will have very bad test error. So this is the same kind of picture as we did, but in reverse. So on the axis over here, it looks like the not U-turn is adding degrees to the polynomial. You'll get the training error down to 0. That is kind of the reverse picture over here, where the size of the window was on the x-axis. And the only difference is which way is the model more flexible. You can kind of think of a small window as more flexible in our problem, and a large polynomial as more flexible in their problem. This is how they talked about it in the videos. Okay, so these are all different ways to see this train versus test error. I'll add one more buzzword to the thing, which is the generalization error. The generalization error. Okay. Yeah.
Sir, in the above graph,
Yeah.
are we making the graph of the polynomial?
No, this is the graph of the root mean squared error. So this is error versus
No,
the degree.
Sir, you said that a polynomial graph will go through each data point.
Yeah, so what let me say that one more time. So if you had a polynomial of degree 30, so x to the 30, and you have 30 data points, there is a theorem in linear algebra that you can find a polynomial that goes through all of them. Maybe it has to be degree 31. Is that what you're going to tell me? Let's see. If you have a line, that's a polynomial of degree 1, you can go through 2 points.
Yes.
Okay, so you only even need a polynomial of degree 29 to go through 30 points. If you have a degree 30 polynomial, there are many polynomials that will go through the points exactly. This is a good point. Yeah, is that what you were going to say?
Yeah.
Okay, great. Yeah, because this is like linear algebra. Any other questions or comments? Okay, let's look. So the last thing I was going to say is the generalization error. And this kind of means different things to different people, but very roughly speaking, it is the difference between, so some people will say it's the true error, some people will say it's the test error, some people will say it's the test error on average, lots of things, but well, let me write down the options. True, or test, or average test, so different people will use this word to mean different things, versus the train. So how is the real error we care about, how is that comparing to the training error? And you can visualize it on this graph as the difference between these two things. So the generalization error is the gap in this picture. How big is the difference? And you can see when you're overfitting, you have a large generalization error. You're getting a lot higher error on the test set than on the training set. That's overfitting. And when you're correctly fitting, then the gap is small, right? So sort of, you want to make this gap small. Note that you don't strictly want to make it as small as possible. So like one reason you could have low generalization error is if you have bad error in both. Then you have like no generalization error. You make the same mistakes on the test set and the training set. That would be like a student who always answers 0. Then he gets a score of 0 on the training set and on the test set. This student is not doing well, even though his generalization error is 0. But it is sometimes something that comes up, and this is like approximately what people mean. And I will say overfitting means big generalization error. This is like another common definition. Overfitting equals large generalization error. Okay. And underfitting is the opposite. This is one way to understand underfitting and overfitting. The other way was the way we talked about with the bias and the variance. Low And once again, this is the surprising thing is that you don't want to go too far either way, right? It's possible to overfit and it's possible to underfit. You want to find the right Goldilocks point in between that is optimal, right? Don't do these are both mistakes. Overfitting is a mistake, underfitting is a mistake. You want to get it right in between at the perfect spot where the error is as small as you can make it. Okay. Any questions about that? Okay, so we've more or less completed thinking about the supervised learning paradigm. Like we have all of the structure. This is like on the first day of the course when I asked you about the Netflix problem. If you want to treat that as a supervised learning problem, we now have all of the sort of steps you would do on the outside of the problem to solve it. So let's sort of like record the whole thing. So this is like the supervised learning, or I'll call this the classic supervised learning paradigm, because you can make it different by doing lots of tricks. Supervised, oh boy. Supervised learning. Okay, so how does it work? Let's call it step 0, because it's sort of before you do anything, is you collect data and you organize the data as X, Y pairs. So it's a list of X, Y pairs. Notice that in real life, you might not actually be given a list of X, Y pairs, right? So for example, in the Netflix problem I gave you guys, I said here is a bunch of movies and users, and it's not true that the movies are the X's and the users are the Y's, or vice versa, right? So if you want to turn something into a supervised learning problem, you got to think of the X's as the inputs and the Y's as the outputs, and just be careful, not every problem in real life is like that. But some of them are, so this is why we do this. So this is the input, and this is the output. And you got to arrange your data like this, where I'm using the input to predict the output, and that's it. So for example, in the Netflix problem, you guys said, let's make a table with like information about the users in the movies. Like we'll write down what genre, we'll write down who is the director. That is converting the problem into a list of X, Y pairs, predict the Y given the X. If the X is all the information about the user in the movie and the Y is like the rating, 1 to 5 stars, then you can treat it like that. Okay, and then this is like the core loop. Let me draw a loop over here, because you can like do testing with this stuff. Let's put it in a big bubble. Okay. Step 1, split into train test. Actually, I guess that's not part of the bubble. Okay. Sorry for those of you with pens who wrote that down. Okay. So you split it up into 2 sets, and then you, step 2, try to find f hat of x using the training set, and then evaluate how good f hat is using the test set. This is the one that you will try a bunch of things. So maybe you'll decide, oh, that didn't quite work. Let me try it again. So you might try step 2 many times. In our particular example, we were doing graphs like this. And a graph like this makes it seem like I did one thing. But actually, for every single time I had a different value of the window size, I had to redo the whole problem, right? You can sort of think of when the window size is 20 and when the window size is 5, you just have to do it all over again. So actually, like this line is like 100 different tries of step 2, trying 100 different window sizes. And so usually there's some parameters you can change. Those things are called hyperparameters. So I'm going to say try many hyperparameters. Hyperparameters. And so in our problem, the thing we've been doing so far, parameters, the hyperparameter was window size. So e.g., we had one hyperparameter, which was the window size. And by trying lots of different window sizes and seeing which ones are the best on the test set, we can kind of get a balance between underfitting and overfitting. We can try to find the thing that works the best on the test set. You can also do more fancy versions of this. So I did train and test, but you could do like this cross-validation, 5-fold cross-validation, where you have 5 different test sets. These are all fancy versions of the same thing. So maybe I could add that to here. Or be fancy, and do k-fold or whatever. But it's all the same idea. I think if you understand it with one trained test set, it's not too hard to do multiple training test sets. Okay, so you take your model, you play with the hyperparameters, you figure out which one is the best using the test set, and once you find the best one, so in our particular case, we say, oh, the best window size is a window size of here, right? This is the best window size is sigma equals 17. Okay, once you find the best thing, then you have the best f hat. There's one last step that is often forgotten, and I asked you guys what this was last time, and nobody knew. So this was the very last question we did almost a week ago, was what is the secret last step that everybody forgets? So once you have found the best hyperparameters, you've figured out your best shot, you've run step 2 hundreds of times, you've like rerun it and run it, made lots of graphs and figured out the best thing. There's one last step that people forget. Yeah?
Finding the accuracy of the model.
So finding the accuracy, by finding the accuracy, do you mean on the test set?
Yeah.
That's in step 2 already, right? So in step 2, we're constantly like testing out the model and we're like fixing it. So we're like, okay, I tried this tweak on the model. I like added 7 to everything. Like, oh, the error went up. Okay, let's try adding 4 instead. Oh, the error went down. Okay, you like do this over and over again. You do lots of, you mess with it. The hyperparameters and the things are changing. By the way, they're not called parameters. I mean, they really are parameters, but parameters is used for something else. So we have to call them hyperparameters. The parameters sometimes live inside a hat. So they're just called hyperparameters. So we're testing it constantly, and I'm saying we already found the minimum. We found the best one we can. Find the best one we can. Find the best one you can. So that's what the loop is. You try it over and over again, and you find the best you can. Okay. And so we're constantly testing it. So that is not what step 3 is. Yeah? Rerun it again on the entire data set. Thank you. This is exactly the one that people often forget. You'll notice over here that the training set is less than all of your data, right? So you've sacrificed some of your data to the gods of overfitting and underfitting to sort of make sure you don't screw up this thing with like confusing the training error and the test error. And that is a sacrifice. Like the f hat you get here from the training set will be less good than the best f hat you can get using the entire data set because you sacrifice some to the test set. And so your very last step is, once you know the best hyperparameters, is rerun f hat using your best hyperparameters. So no more experimenting. You rerun it on the entire set you have, and your best hyperparameters on the entire data set. And that will be the best thing you can sort of do. Okay. So there's the kind of like supervised learning paradigm in one page. Questions or comments about that? Okay, so far, the only thing we have done is f hat using this nearest neighbor averaging model, which is kind of a silly model. We're going to go over it in a second. The nearest neighbor averaging is a great instructive model to like understand overfitting and underfitting. I think it's the best way to understand overfitting and underfitting. You can visually see it overfitting. Like you look at this graph and you're like, that is obviously overfitting. Like you get a visceral sense of this model is overfitting, and you can understand why. We're going to move now to harder things, where it's harder to see if it's overfitting or underfitting, but everything still works. So that's the point of doing all this stuff, is everything we learned will still apply, and this will still be the same thing. What's going to change is in the guts of step 2 over here, when you change to a different type of f hat, you get different stories. So sort of a lot of the rest of the course is going to be trying different f hats. Everything else will be the same. The whole like setup is the same, but we're gonna like focus in on how do you choose a different f hat? What could you choose other than this averaging thing? And you'll see there's many, many hyperparameters. So in the example we gave, there's one hyperparameter, but in real life there's like could be thousands of hyperparameters. How do you figure them out? Yeah.
Sorry, on the last step, so when we found, I know we re-estimated everything the entire data set, and the mean square error for that one is significantly different from what we got as our best mean square error. What happens then? We have to then start.
Okay, this is a good point. So when you're doing step 2, you're going to have a training error and a testing error. In step 3, you will only have a training error. You will not have a testing error. So at the end of step 3, you don't actually know how well your model will do, right? You have no test error. Your best guess for how the model will do would be, oh, well, I tried it in step 2 and I got this much test error. So if someone says, how good do you think your model is at the end, your best bet is actually to say, well, my step 2 error was this much, my test error. That's my best guess. It is true if the training error in step 2 could be compared to the training error of step 3. If the training error in step 2 is very different than the training error in step 3, that might be a sign that something went wrong. Because you're kind of hoping that step 3 is just like a slightly better version of step 2. And if the training errors are like wildly different, then like maybe something broke. Maybe there's like some weird point or like a bug or something. But it's true, you don't know how good it is. So remark, because you have no test set, remark, no test error in step 3. So the test error, like when you're making choices, you want to have a test error so you can make better or worse choices. In step 3, you're just trying your best. You don't know how good it's going to be. No test error in step 3. Okay, yeah, fantastic question. Anyone else? Yeah.
Sir, if the accuracy comes same after we run the same model, so can we say that it is overfitted or underfitted?
If the so again, accuracy is the same kind of word as error. And the problem with both the word accuracy and the word error is you cannot say error on its own because we have like 3 different types of error. So when you say the accuracy is blah, which accuracy are you talking about?
Test accuracy.
So if the test accuracy does what?
Comes same after 2-3 times running the model. For example, it is coming 95%, 4 or 5 times or 7 or 8 times.
But so what do you mean by, so you mean you're like doing this loop of trying to improve it and it's not changing? Yeah, so when you're doing the loop, you're trying to make the accuracy as high as possible. At some point, you're going to say, this is the highest I can make it. And then you are done in step 2. You move on to step 3. So when you're doing this loop of trying different things, you're trying to make the error as small as you can, or equivalently, the accuracy as high as you can. And by that, I mean the test accuracy or the test error. And at some point, you have to give up. And you say, like, this is due tomorrow, so like we're done. That's what you do. Yeah. Okay, any other? Let me motivate you a little bit to ask some more questions. The first project in the course is due in like 2.5 weeks, 2 weeks from Friday. In the first project, you will do this. You will do this. I wrote up briefly the instructions for the project. Let me open that up. So on CourseLink, you're going to exactly do all these steps. Let me open it up. You can also read about some problem-solving tips while I'm getting it ready. Okay, so this is on the website, and it will be public soon. Right now it is private, or it's hidden from you because I'm making some last-second changes. Your first project, you're going to have a housing data set. So you're going to have a bunch of houses. I did step 0 for you. You're going to have 2 files, housing data train and housing data test. Okay. So if we go here, I did step 0 for you. I collected a bunch of XY pairs. The Y is how much the house sold for. What was the price of the house when it sold? And the X is a bunch of information about the house. Like how many square feet, how many bedrooms, where is it, that kind of thing. How many bathrooms, stuff like that. That's going to be X. And then your job is going to be to do all of this stuff. And after step 3, we're going to add a secret step 4, which does not happen in real life, but does happen when you take a course, which is step 4. So this doesn't happen in real life, but it happens in this class. The professor grades your answer. Grades your answer. Okay, and how am I going to grade your answer? Well, I have some held out secret data. So I have using X, Y, not given to you. Not given to you. Okay, so I held out some data. I didn't give you all of my data. I kept some of it secret. And in particular, I will give you the X values, but not the Y values. So the X is given to you. And this is not given to you. Okay, so there's two data sets in this thing, because step 0, that's like the training data set. That's like really what you want. That's what's given to you like a real life problem. And then at the end in step 4 is just my grading data set, where I don't tell you the Y values, and you're going to predict what you think the Y values are, and I will tell you what your score is. And in fact, the score is going to go on a leaderboard. So you submit, and you can see how everybody else is doing. You can put in a fun nickname if you want, and we'll see who gets the lowest score. Okay? Well, the lowest error. Remember, you want the error to be small. This is like how far off are you? You want that to be as small as possible. So that is what you will do. You'll do all these steps, and then you will submit. There's going to be a website where you can submit your predictions for what you think is going on. I'll show you how to do that in more detail later. But that's what you'll do. Okay, and there's some more details on what you have to do. So you're going to submit a Python notebook that shows all the steps you did. And in particular, the thing that is different in project 1 than the other projects is you need to show me overfitting versus underfitting in your project. So I want you to show me in the details of step 2, when you do step 2, I want you to show me, you're like, I tried it like this and it was underfitting. And you're gonna say, I tried it like that and it was overfitting. And then I did in between and it works so well. Look at how beautiful. That's what you're gonna show me. And you're gonna show me, you're gonna make a graph just like this graph. And you're gonna show me this graph in your project. You're gonna be like, look, over here it's overfitting. Over there it's underfitting. Here's how I found the thing in between. That's what you're gonna do. Okay. What else is there to say? So I'll post this soon. And then you'll have the final model and like how well you do, how performant your model is. The leaderboard is just for fun, but if your model sucks and is really doing a bad job, that will affect your grade in the final model. I kind of know the best possible model, so you're gonna be compared to like reality, not the other students in the class. The leaderboard's just for fun, but your actual scores do matter. And you're also gonna write a nice like summary that is readable to people who are not data scientists. In 2 weeks, you have to submit a draft, and then you will have like you'll have a week where we give you feedback, and you'll have a chance to make changes. In the final project, you'll also do a little video walkthrough. So you record yourself talking for 5 to 10 minutes about your project and what you did. That will be the first project. So I'll post this. You'll have a chance to read it carefully and ask detailed questions for sure. But are there any like high-level questions or comments about the project? Yeah.
Are we restricted to use linear neighbors?
You are not, and in fact, most people use linear regression, which is what we will do in the next week or so. And I will even tell you what kind of knobs you can turn for linear regression, which is related to this kind of idea of like the sort of the degree of the polynomial, like the number of different things you input. That is the kind of thing you will do. So almost everybody does linear regression, which if you've never seen linear regression, you will know in a week or so how to do. Okay. Other questions or comments? Okay. Yeah.
I have a problem of the previous question.
Yeah.
The steps. Like in step 3, you're also including the test data set for sort of examining your model.
That's right.
But I feel like it is very possible that you will get a higher error.
Oh, okay. This is okay. This is a good point. Let me actually make one thing really clear here. So in the actual project, like your project 1, you have your data. This is technically all training data, and then this split. Sometimes we will call this a validation set to not get it mixed up with the test set in step 4, right? So in quote real life, like after step 3, you will not really know like how well it's doing because there's no test set. But in project 1, you can submit it to the leaderboard and I will tell you the score. So you sort of have there's like this extra thing going on. And so like if your model, you can check, this will be a good practice for you guys. You can compare the tests that you get during step 2, that's some error. And in step 3, you'll get some error from me on the leaderboard. you can compare and see how different those are. And if they're very different, maybe it means something's not working the way you think it is. Yeah. I'm not sure if that answers your question. You're asking like a more broad question, not just on project 1.
No, I mean, what if you get a higher training error in step 3 compared to the step 2? How do you deal with that part of the error? Do you just leave it here?
I think you just leave it, yeah. So if it's very different, this might be a flag to you, like maybe something is broken, I should go check.
Okay.
But if you check and nothing is broken, then this is a higher training error. Yeah.
Thank you.
Yeah.
So is that the given test set was for step 4 and the given training set was for step 2?
Yeah, so you are given in the project, you're given the XY pairs in step 0, and you're given the X's in step 4, but not the Y's. I have the Y's. Yeah. In fact, I could have asked you I could have not even given you the X's. I could have said, please just give me your model. Like, tell me what the function f does, and I will run it. But that's too much work for me, so I give you the X's. You run it on yourself, and you tell me the Y's. Okay.
Sir,
Yeah.
so the y values doesn't have to be exactly the same as O, right?
No, right. So you get graded by the error, like how far you are in root mean squared error.
Okay.
So the leaderboard will say, what was your root mean squared error, and you want to make that as small as possible. That's right. Okay. Okay, so any other questions or comments? So that's kind of what we've been doing so far in the course, is setting up this whole thing. We've done the example of the nearby neighbor averaging inside step 2, because nearby neighbor averaging is the most intuitive model. You can see the picture, underfitting and overfitting, hopefully make perfect sense now. In the next week or so, we're gonna replace the nearby neighbor model with linear regression. We're gonna do some linear regression stuff. You've probably seen linear regression before, but it's a good refresher. And in particular, we're going to play with different hyperparameters to see how we get underfitting and overfitting in linear regression. That's where we're going. And then at the end of that, you're going to know all this stuff. You're going to know how to do linear regression. Your project 1 is putting those two things together. Okay. Questions or comments? So we're going to start linear regression now. That's the next big topic. Okay. Let's do some linear regression. So in Mathematize, I have so hopefully you've watched the videos. Let me point out why people like linear regression. So linear regression is also sometimes called least squares, or ordinary linear regression, or ordinary least squares. And that's because you can add on weird stuff to linear regression to make it slightly different. So one thing we'll do later in the course is subset selection and lasso and stuff. We will do that later, but least squares means linear regression. And the nice thing about linear regression is it has good interpretability. That's the thing that was missing. So in our nearest neighbor averaging model, you might notice that there's no explanation for what you get. So for example, in this particular example, if I were to, let me make it a little bit less silly. Okay, so it's like this. If you say, why did I get an estimate over here of this much? Well, the answer is, I don't know, there were points nearby that averaged out to this much. It's not a very satisfying explanation. In your housing data set, you'll say, why did you predict that this house was worth $300,000? And you'll say, I don't know, that's just like what it came out to. We averaged some stuff, and it did. In linear regression, you have some interpretability. And the interpretability is because you have these linear coefficients, the coefficients that go in front of everything, and you can use those as explainers. So when someone says, why did this house sell for, why do you think it sells for $300,000? You'll say, oh, the reason is because it's 4 bathrooms, and a bathroom is this much, and it's this much square footage, and that sells for this much. And you can kind of get a feel for why you're getting the outputs that you get. So this is the reason we're going towards linear regression. It's better than least squares. Or better than, sorry, the nearby neighbor averaging. There is one other reason that this kind of picture is not good for real life problems. I think they mention it in the videos. Does anybody know why can't you do nearby neighbor averaging in quote real life? Why is it only good for as a toy example in your data science class? Does anyone know why? Okay, the reason is this model is great for one-dimensional things when you only have one x input, but is not good when x is very high dimensional. And that is because when things are high dimensional, the test points, or the points you're given, are very far apart. So in one-dimensional space, shooting the cannon at 10 degrees and shooting it at 12 degrees should be very related. But in real life, you have like 10 different dimensions, right? So you're gonna have a house, and the nearest neighbor house will be a very different house. It'll have a different square footage, it'll have different number of bedrooms and bathrooms. So in one dimension, things can be close together, and that's good. But in high dimensions, the nearest thing is quite far away. So this does not scale well with dimension, whereas linear regression is really good at scaling with dimension. So when you go up to higher dimensions, linear regression still works very well. And that's the real reason we're doing it. So it's not on this graph, but flexibility and interpretability are one thing. You also need a check mark. Does it work with high dimensional data? And as like data sets get bigger and bigger, things that work well with high dimensional data seem to be better and better. And in particular, like deep learning, like machine learning methods, I think that's the secret why they're so good. They're really good at high dimensional stuff. Whereas stuff like this is terrible at high dimensional stuff, and linear regression is somewhere in between. It's pretty good at high dimensional stuff. It can get swamped if it's too high dimensional. But that's why we're switching to linear regression. Okay, what else do I have for you? Okay, so when you're doing this thing, you're taking advantage of interpretability. One of the dimensions are these so-called standard errors and understanding significance. And so that's what we're going to talk about now. We're going to talk about confidence intervals. And we're going to build up to doing it for linear regression. But I want to start off with like a stats 101 question about confidence intervals. And so here is my stats 101 question. Just like we started with dice rolls, right? We're starting with 100 independent mean zero variance one Gaussian random variables. So these are these bell curve distributions, and then I'm averaging them up. A stands for average. Add up 100 of them and divide by 100. That's their average. And the question for you is, can you figure out the average value of A? And can you tell me a 95% confidence interval for A? Because when you do linear regression, these kinds of confidence intervals are one of the reasons they're good. So let's do this problem. Hopefully as a review from your stats class. And we'll take it up in, say, 2 or 3 minutes. 5 people have answered. Who needs? Let's see what you guys put. Put in some guesses. I want to see like how close people are. Put in whatever you can. If you have no idea for something, that's okay too. Put in, let's say 111. Number 111 will be code for I have no idea. Put in whatever you can, and I'll see how people are doing. So put in your guesses, even if you're not sure what's going on here. Okay, and I'll give you like 10 more seconds to do that while I fix this. Okay. Okay, there's like 5 people who haven't answered. Put in your guesses. Okay, I have to put up a timer, and I have to say 10 seconds. That way everybody will panic and answer. Put in your guess. When this beeps, I'm going to press the button. Okay, here we go. Okay. We're doing it. Okay. All right, let's start with the mean. So the mean is the kind of thing we were talking about before. The answer is 0. If you have things that are mean 0 and you add them up, it still means 0. So very good. That was that big bold E we did in the first few classes. The real question is the confidence interval. Okay? Let's see what you guys think for the confidence interval. On the left side, some people think it's negative 0.196. Some people think it's this. I guess the computer is like has some error tolerance. Some people think it's positive 0.196. Some people think it's negative 0.02. Look, there's a 0.0. And some people think it's negative 2. Okay, this is great. So let me tell you the facts. This is the one fact you should know about Gaussian random variables, right? So you have a bell curve. This is what you should have learned in your Stats 101 class. Here's your bell curve. The 95% interval for mean 0 variance 1, which you write like this, is minus 2 to 2. Minus 2 to 2. Or, if you want to be more precise, you could say minus 1.96 to plus 1.96. So that is if you have a single variable. So 95% of the time, it's between minus 2 and 2. I'm gonna say minus 2 to 2 just to be a little bit faster. 95% of the time is somewhere in here. Okay, great. That's 95% of what it is. So that is the fact, and I think most people remembered that because they had numbers involving this minus 1.96. So the only question really is, when you average up 100 of them, what happens? So when you average 100 of these, what happens? Okay, and basically, inside the answers, there were a few different possible answers. Some people said, okay, well, you're averaging 100 of these, so you divide it by 100. So one possibility is that it shrinks by a factor of 100, right? So then you get 100 times smaller. Let me draw it 100 times smaller. So this is a times 100 reduction. And that would be like that, okay? And you get minus 0.02 to plus 0.02. That could be what some people said. Or another thing that some people said is a times 10 reduction. Okay, and a times 10 reduction would be minus 0.2 to plus 0.2. Okay. Did anybody? Oh, I guess some people said nothing happens. You average them, you still get this. So a times 1 reduction. Times 1. So this is like nothing happens. Let me write nothing happens. Nothing happens. Times 1. Okay, then it's exactly the same as it was before. Okay, so minus 2 to 2. Okay, those are the 3 options. Nothing happens, times 10, or times 100. Was there anything else? So presumably on the other side, people did it this way. So some people said nothing happens. Some people said a 10x reduction. Some people said a 100x reduction. Which one is it? Okay, and I will let you revote now that you've seen the picture. Maybe this jogs your memory. Feel free to chat with the people near you. Try to figure it out. Each one of those 3 things. Okay? Let's revote this. And I want to do it relatively quick. So I'm just going to give you 1 minute. You have to pick. Let me Let me make it its own question. Okay, so I'm gonna give you 1 minute. I'm gonna make a new little question here. If I can. So let me start the timer for you. So go chat with your neighbors for 1 minute. Okay, I made it a multiple choice question. You have option A, option B, or option C. Option A is a 100x decrease. Option B is a 10x decrease, and option C is nothing. So you tell me, is it option A or B or C? Let's give 1 more minute since I just got this going. But put in your guess. There we go. A or B or C? And I want to present this. Okay.
Excuse me, sir.
Yeah.
Sir, actually, there's usually calculating the confidential level values by this formula, where X is the sample mean, sample size, and the standard deviation.
The formula you are using works sometimes.
Okay, but not every time.
It works as long as things are Gaussian, which they are in this case.
Yes, so
Yeah.
for this I was getting plus minus 9.5.
Then you've made a mistake. Okay. Yeah. Okay. I'll show you how I did it in a second. Okay. Let's stop and let's see what you guys said.
मैंने formula कुछ गड़बड़ use किया है.
Let's reveal. What did people say? B and C are equally split. Some people think it's B. Some people think it's C. The correct answer. Oh, it doesn't know the correct answer because I just made this up now. The correct answer is B. So if you chose B, you got it right. It is a 10x reduction. The correct answer is negative 0.2 to plus 0.2. How could you do this problem? Well, in general, you have to kind of know this fact. I did this fact for ordinary Gaussian with mean 0 and variance 1, and it was from -2 to 2. In general, if you have mean mu and variance sigma squared, the confidence interval is mu minus 2 sigma to mu plus 2 sigma. So this is the kind of, if you take this thing and you stretch it out and move it left or right, you get the general idea. And then the question becomes, what is the variance? What is the variance? The variance is sigma squared for A, which is the sum of 100 things. What do I call them? Xi's? Okay. So if you know the variance, if you take the square root of the variance, that tells you how far you need to go. Okay? The square root of the variance tells you how far you need to go. So you need to do the mean and the variance for A. The mean we already did. The mean of A is 1 over 100 times the sum of the means of the xi's. And those were all 0. You're adding up 0 100 times, you get 0. Most people got that one right. The variance is a little bit trickier. The variance of A. What is the variance of A? We did this in class a few weeks ago. We had the sum of a bunch of things, and we did the variance. If you do the variance, that's the same thing as the expected value of A squared minus the expected value of A. So it involves squaring this thing up. And when you square this thing up, you will get a Pythagoras formula for expected values. So I will sort of skip the details because we did them before. But the punchline is by Pythagoras again. That's why I show everybody Pythagoras for random variables. And the details are typed up on the website. This is going to be 1 over 100 squared. The 100 becomes a 100 squared because of the square thing. And then you're going to have the sum from I equals 1 to 100 of the variance of xi. So variance goes with the square, but you can add them up. But that's exactly Pythagoras. And 1 over 100 squared times the sum of 100 things is 1 over 100 squared times 100 times the variance of every individual guy. They're all equal, and they're all equal to 1. Let me write down 1 times 1, which is 1 over 100. So when you take the average, the variance gets 100 times smaller. And if the variance gets 100 times smaller, sigma is the square root of the variance. You get the square root of 1 over 100, which is 1/10. So the size of the interval, it used to be minus 2 to 2. Now it is shrunk down by a factor of 10. It's the square root. This is a very common thing that happens in probability. Things go by the square or the square root, according to the central limit theorem. And in this situation, what's going to happen is the minus 2 to 2, that was for a single mean 0, variance 1. A is going to be mean 0 and variance 1/10, and that has a confidence interval of minus 0.2 to plus 0.2. Okay, so that's one thing to sort of have a basic knowledge of the theory and be able to calculate this kind of thing. And the other thing you need to do is sort of understand what it means. And I made a little notebook with experiments to understand what it means. This is a 95% confidence interval, which means if you sort of repeat the experiment 20 times, the mean should be between minus 0.2 and plus 0.2, 19 times out of 20. So let's see if it works. So I made this little experiment notebook over here with like the most basic experiments you can do with this stuff. And here's what I did. So I have 100 Gaussians. The standard error, that's exactly what I calculated. Look, I'm using 1 over the square root. That's exactly what I calculated with pen and paper, and I've just coded it in the final answer. And here is the confidence interval and the number of things to average, and it came out to exactly to minus 0.2 to 0.2. But now here's the fun part. I ran it 100 times, or not 100 times, just 20 times, and I reported what is the real average of doing it. And here are some answers: 0.08, negative 0.03, negative 0.07. And I asked the question, is it in the 95% confidence interval? And if I did things correctly, approximately 19 of these should say true, and approximately 1 of them should say false. So let's see, did one of them come out false? True, 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 true. They all came out true. Okay, we got to rerun it. Let's run it again and see. So on average, 19 of them are true, and 1 of them is false, hopefully. Okay. Let's run it again. Okay. This time, true, 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 true. Ah! Give me a false. Ah, there it is. Okay, look. All right. So is that 1 out of 20 is false? No, that's actually 1 out of 60 has been false, right? I ran it 3 times. Look, we have to run it a million times and see what fraction. Is this one going to have more than 1 false?
Yeah.
This one has 1. Okay. So that's the idea, is that it should be 1 out of 20. Right now we're at 2 out of 80. If we keep running it, eventually we should get close to it. But that's what it means, and that's what the calculation says. Any questions or comments about that? Why is it important to understand this stuff? Well, when we run linear regression, there's also formulas for the confidence interval for each of the coefficients. So if you scroll down into the rest of this notebook, there's a simple linear regression. This is like 1 x value and 1 y, the simplest possible x and y thing. And at the end of the thing, we're going to have the same kind of situation. So I'm going to show you the final answer, and then I'll explain it probably in that video next class. If you rerun a linear regression 20 times, then 19 times out of 20, it should sort of be in this box. And 1 time out of 20, it should be slightly out of the box. And that kind of tells you, when you run a linear regression, how close you are to the true values that you're looking for. So in this particular example, the true value is 3, 2. And 19 times out of 20, when you run your linear regression, you're close. And close means you can calculate how close. Close means 1 time out of 20, you're outside of the box. In this situation, it was actually, okay, well, I won't say, it's actually 1.5 times out of 20 that's outside the box, but I'll explain why next time. So this will all be in the video, I think, next class on this basic linear regression stuff. And then when we get back, we will do multiple linear regression. So in multiple dimensions, things get even crazier, and you need to be able to handle that. But okay, that's where we are for now. Do keep an eye out. I will post a video for Wednesday's class. Don't come here in person. And I will probably also slightly modify the video schedule. So also watch out for that. Other than that, let's stop there. If you have questions or comments, feel free to come ask me.